I'm going to talk about a couple of things today. Before I start sharing what's going on, I did just think it would be worthwhile showing where I am at the moment up here and at the top of the world there in Australia, and you guys are down there. So basically, we are almost directly the opposite of the world, and to be able to share some stuff in real time is pretty amazing. I'm going to talk about communication in my talk. Okay, so that's a list of some of the projects that I've worked on over many years, and I really enjoy working on these types of buildings as they're big enough to warrant some effort being put into the optimisation of the design. This might be in tonnage of steel or design for constructability or lots of other things you get to investigate. On day 3, Nook is going to talk through what's next around innovative structures. So I'm going to go through some of the innovations that have allowed some of these projects to come to fruition. So I'll also talk about some of the changes that have happened in the world that we've been able to leverage off to produce those designs as well. So I'll loosely cover those 4 topics on the screen. I'll start with what's now called Marble Stadium, which is a project here in Melbourne, for which we had a structural sub-consultant, Modus, which is based in Manchester. Some of the facts and the figures of the stadium are there. It was opened in March 2000, and that's actually an older photo. It's pretty hard to get a good image of that facility now. It's because it's actually been surrounded by multi-storey buildings. The main feature of this stadium is its operable roof. It has 2 panels, each of 167 metres by 54 metres. And the cool thing about this project was the roof was actually constructed on the ground outside the stadium, hoisted into place in sections that were driven on temporary rails, and then the next section of the roof was constructed in the same spot, hoisted up and then driven as well. So a lot of work went into working out how to make all that work. Interestingly, when you're dealing with huge structures like this, you end up with some pretty large deflections, and we identified that when we lifted this structure up, it was going to, did actually deflect by about 480 millimetres vertically, because the roof plane is actually arched and elongated. It rotated because the arching truss over the top was not symmetrical, and it also bowed horizontally because of the asymmetric loading on it. So we did a lot of work before we actually lifted the thing up, and to predict what these movements actually were, and we're pretty chuffed with how close we actually got to the actual deflections when it lifted. So I mentioned communications at the start. For the design of that stadium, I was in nightly contact with our team in Manchester, and that was via a thing called fax. And I would collect up all my queries from my team and I at the end of each day, and we'd handwrite or sketch them out, pop them onto the fax machine, and hope that the answer would be waiting for me when I came in the next morning. When it worked out great, it was great, but when it didn't, I knew I was going to be in for a bad day. So nowadays, with Zoom and MS Teams and the ability to share large files and things, so much easier. A good recent example is when we were chasing a project in New Zealand a couple of months ago, and we were workshopping ideas with people in London, Singapore, Melbourne and Christchurch in real time. So the ability to be able to do that has been a game changer, and that certainly encourages and facilitates the ability to JV on projects. One of the biggest advances in the design of long-span structures are some of the cool toys we get to play with. With that, it's enabled us to explore many more options much more quickly. So let's have a look at the Perth Arena, 14,000 seat stadium. It's got an operable roof that's able to support 85 tonnes. And the external facade of that was based on a number of quite unique structures that were actually 3D shapes that were based on something called an infinity puzzle. You can Google that from about 2000. It was what the background to the infinity puzzle was, but the architect said, we're going to take shapes of that and we're going to make a building out of it. So it was, initially we thought, well, how the hell are we going to attack this? And the answer was it was my first use of Rhino. And what we did was I went around to the architect's office and we just sat for hours in front of the computer running through the model and trying to work out where we could put columns, because many of those shapes were reflected on the interior concourses as well. So there's many sloping columns and obstacles that we had to get around, and so sort that out using programs like Rhino was a huge advance for us. And then I think it's these major projects that drag designers into these new technologies, and now obviously Rhino Grasshopper is pretty widely used. This arena featured an operable roof supported on 2 trusses that were 10 metres deep and spanned about 110 metres. And the contractor elected to fabricate that sort of 110 metre by roughly 40 metre assembly on the left-hand side there in the plan. Assemble that on the ground and then hoist it all up. So this saved a huge amount of erection time in the air. It meant that the arena seating and concourse below couldn't be commenced until the roof was out of the way. Now I think Angus will probably touch on this subject a bit later today, but knowing how these big structures are going to be built can have a big influence on the design of long-span structures. As they're often fabricated in sections and temporarily supported by intermediate columns and the like, you also have got to think about lock-in stresses that can be caused during the erection process, and that can in fact have an influence on the design of the actual members themselves, and their worst case load might actually be during that erection procedure, and I'll touch on that a little bit later. And as video games and the like became much more interactive and user-friendly, so did our analysis tools. Changes from inputting coordinates through spreadsheets and the like to graphical interfaces really helped us speed us up as well. I'm going to show a little video here, which I'm hoping will come through okay. And this is of a study that I got one of our designers to do to backwork the design of one of the main trusses on Marvel Stadium, just to show in real time how we can start with a set of variable parameters and come up with the best design based on the criteria that we choose. Now, I use the word best design carefully there. It could be the least amount of weight, or it might be minimising the fabrication weld time, or it might be the CO2 emissions associated with supply and fabrication and erection of that member. And what you're seeing, I'm hoping you're seeing, is a real-time analysis of multiple options being tested and homing in on the preferred solution using Crumbler. These tools can be very powerful, but can also suck young designers down some rabbit holes, and they can really start wasting time as well. So I'm a firm believer that in being very hands-on and not just analysing for analysis' sake. Federated models and clash detection is another example where tools can be used to refine and coordinate designs when they're used wisely. having workflows that enable architects and engineers to regularly share and update models seems great in principle until the architect shifts the wall and takes one of our columns with it and doesn't let us know. So, with those workflows and things, you definitely need to agree the protocols and not just allow willy-nilly changes, which some of our eager and enthusiastic designers might let slip through. And another problem with federated models is that everyone becomes an expert. So many times we've been in client presentations and we're trying to explain the structure, knowing that the MEP documentation program is lagging behind ours, but we'll be constantly picked up for pipes missing penetrations or flipping columns and things. And that's exactly what happened in a job I did recently in Qatar, from which those couple of examples are from. So look, I've already mentioned the erection methodology for Perth Arena on the left there, and also for the operable roof for Marvel Stadium. And as I said, for Perth, it meant that the construction of part of the seating pole needed to wait until the roof was actually raised. For Marvel Stadium, for that operable roof, because there was space next to the stadium, we could do it out there, but that space wasn't big enough to fabricate the full roof panel, which is 54 metres wide and 167 metres long. So we had to do it in two halves, which is 167 by 27 metre panels. So this meant that the construction inside the stadium wasn't hampered, but large temporary rails were needed to extend the permanent running rails to connect the jacking towers to the edge of the curved stadium. So, there was a fair bit of cost involved in some of that temporary steelwork that was required. For the fixed roof at the Marvel Stadium, the left-hand side there, that's an image of the northern roof. And the red-coloured steel you can see there is temporary support towers, and they were put up to support the lower triangular portion, which was continuous. And you see up over the top of that, lower portion, there's half of an arch that's been erected, and there's another half that's going to go on later. And you can see there that the secondary trusses are going in at the same time as well. The same sort of approach was used on the eastern side, which is this image on the right-hand side there. And that's a truss that spans 150 metres and supports some secondary trusses that span up to 50 metres. So due to the cantilever leading edge on that, it's got a load, that 150 metre spanning truss. Spanning truss has a load width of almost 40 metres. One of the things that our analysis programs do for us is just assume that everything's suddenly fabricated in a gravity-less environment and then magically plop down on site. But in reality, these big sorts of projects can't be built that way, and they have to be fabricated in segments. So for that 150 metre spanning truss, we actually fabricated that in 37.5 metre sections on the ground, and then for stability of those sections, some of the trusses coming out of the page had to be installed, and then of course for stability of those secondary trusses, they needed to start putting some bracing and things on them, and then of course builders being builders, they started loading those structures up. Now they're doing all that while we had these 37.5 metre portions of structure being done. And the engineers amongst the audience will sort of understand the bending moment diagram that would be associated with a four-span continuous member like that. But of course, the next step is that you've got to put that bottom chord in, and when you are loading up that top chord member with the secondary structure, and then putting in that bowstring tension structure, you have a series of tension and compression stresses that you need to understand how they're going to either be locked into the structure or get out of the structure. If you ever got the opportunity to design something big like this, you'll find yourself debating the implications of those lock-in stresses with your colleagues. And good luck, because it's some really good, robust discussions you'll have. And it really makes you think, and you need to fully understand each step of the construction process. And then you'll also have to debate the effective length of that bottom chord under uplift. That's a cross-section through that truss, and towards the end spans, you can imagine these members are actually quite steep. That lower chord bowstring will be up here somewhere, and you can just see that that's nice and stable. But towards the centre, where the section's taken, these members have got pins top and bottom, so you've got to determine what is the effective length of that bottom chord in an uplift situation. And once again, I'll leave you to debate that one. All I'll say is it's been there for over 20 years and it hasn't buckled yet. You also need to consider how you're going to take those propping towers out. That top chord truss is actually about 3 metres wide, and the props were about 30 metres tall. So they're pretty substantial structures in themselves. And based on the imposed load at the time of depropping, we expected the truss would deflect by about 250 millimetres in the mid-span. So we solved the problem of getting those temporary towers out by including jacks into the propping tower, so that we could progressively release them in about 30 millimetre increments until the truss was free span. Once again, it's just interesting. You really need to understand every step of the erection process so that little things like that aren't missed. And a deflection of 250 millimetres isn't bad over that sort of span. But we've done projects where deflections of over 1 metre were expected, and that's when you really need to be confident that you understand what that sort of movement is going to mean. If you're getting those sorts of deflections, you probably need to understand the natural frequency of the structure as well, and to determine whether it's a wind-sensitive structure. That's probably not a topic. It's a whole topic in itself. So enough for that for the moment. Wembley is actually another project that I think a number of people on the call will know. It's a project that I worked on that had a pretty interesting roof erection methodology that significantly impacted the construction program for the grandstand structure. I think Angus might speak a little bit about this a bit later today, so once again I won't cover it in detail, but I will note that the erection methodology for that was always known from day one that was going to be very complex for this stadium, and just to reiterate that it's super critical on these major projects that all members of the design team, the construction team, the programmers, suppliers, fabricators, everyone just needs to be on the same page. Everyone needs to understand the complexities and make the appropriate allowances. Wembley's got a fantastic operable moving roof system. There's 7 unique panels and all quite complex, and that was a section of the project that I was mostly involved in, and spent a little bit of time in London for it, so happy to have been involved. In 2018, I spent a fair bit of time in Qatar. Not allowed to share any images of that project, but I found a good sketch on good old Dr. Google that explains the roof concept that's being used on that project. It's It has an average external diameter of just over 300 metres and an internal opening diameter of about 100 metres. That's a little bit out of scale, that little sketch. A big advantage of this type of structure is that the actual erection time can be quite fast, and being towards the end of the construction program, there's plenty of time to get the design right. But the downside is that the grandstand needs to be essentially complete before the roof construction starts. And apart from the compression ring which can get built at the back of the seating tier. And the equipment required to string and raise the cable net is very big and very expensive. Nevertheless, that is going to look magic when it gets completed later this year. So till now I've been talking about what we've done, but let's now think about why we're doing it. And that's the drivers behind this. The old grandstands at most old stadiums had roofs that were supported by columns at the front, but these are just not acceptable these days, necessitating more elaborate roofing systems. Once a cantilever gets above about 25 metres, the mass to span ratio starts to shoot up. So we need to look at alternative load paths or long span structures. Because these are expensive structures, they need to produce more income. A stadium can't just rely on a football match every second weekend to sustain the operational costs. So everyone wants to build a multi-purpose facility that can generate income from other sports, concerts, conventions, rave parties, etc. So the next step is then to looking to control the environment by providing a full roof. But this won't let the grass grow, so then you need to start making it operable. And the broadcasters don't like shadows and rain, so they want to be able to play the games with the roof closed as well. So there's always some reason why we need to do the next best thing, the next biggest thing. The driver for Rod Laver Arena, which is the venue for the Australian Tennis Open, was that it was built in the 80s. It had an old roof that was regularly breaking down. And on a really good day, it took nearly 30 minutes to close. So that meant if it rained during a tennis match, the broadcasters had to come up with some filling information, for 30 minutes, and people would switch off. So we actually went to our client on that project and said, we can make your roof go 5 times faster, more than 5 times faster. And that was just a game changer for them, because it meant that if it rains now, the broadcast can basically go to an ad break, and when they come back live, the match is almost ready to start. So that was the driver behind that project. The driver for Margaret Court Arena was that the architects on that one just wanted to be different to all the other stadia and with operable roofs in Australia that they've seen, and particularly through the US. Typically, the projects to that date were big visual elements that stood out for kilometres and celebrated the brute strength of the steel. So the architectural inspiration for Margaret Court Arena was a car sunroof. They wanted a roof that, when closed, just looked like a fixed roof. In the end, on that project, we were able to get the distance from the top of the operable roof to the top of the fixed roof down to about 1,200 millimetres. So certainly achieved the result they were looking for. John Cain Arena in Melbourne is the 5th major sporting facility in Australia that features an operable roof. Aurecon's been involved in all 5 of these designs, providing both structural design and the drive mechanism design. In fact, one of my mechanical engineering colleagues and myself have been involved in them all. A really cool feature of this building is that it houses an international grade velodrome. These two photos are actually taken from the same location or similar location where those seats over the far side there are actually those same seats there. And the seats on the left-hand side in the right-hand photo are actually hanging off the roof in the photo on the left-hand side, and I'll show you that a bit more clearly in the next slide. So in this image, the operable roof panels are shown in blue. They slide left to right across the page. The cycling track is shown in yellow, and the seating tiers are shown in that greeny colour, with the shown set up in an end stage condensate mode, with the stage being able to be placed on the right-hand side and seating on three sides for that mode. So the roof, fixed roof structure in that building had to be designed to support the operable roof structure, plus the seats when they rotated up to the roof, plus theatrical loads and concert loads to be able to hang off both the underside of the seats and the operable roof panels as well. So definitely a very versatile multi-purpose arena in that project. So what is the next big challenge for structural engineers? What is the next big driver? It could be a raisable pitch, which is something we actually looked at for a recent project. The advantage of this was that for a concert mode, there would be great acoustics and plenty of structure to hang concert rigging loads from the underside of. And in this mode, the grass would have unobstructed access to sunlight and wouldn't be damaged by the concert goers. The downside was the weight that had to be raised and lowered, and the amount of steelwork around the perimeter supporting trusses to carry this load was pretty big. Producing arenas that can be truly multi-purpose is the holy grail here, so this concept is definitely worth pursuing. Maybe one day we'll get it up. Something that's getting a bit more attention these days is not just to do things because we can. Right-sizing a stadium in the first place is a good start. Don't build a stadium with 40,000 seats just because it might host a FIFA-sanctioned event one day well into the future. If the client only needs a 25,000 seats stadium, then build just that. It'll be cheaper to build and won't be wasting resources. So are there other decisions that can be made that will reduce the impact on the environment, or even better, reverse some of the negative impacts that our industry has caused in the past? There are going to be a few sessions over the next 2 days that will touch on those topics, and I'll be keen to see where the discussion goes on that topic. Globalisation. Historically, Australia has had a fairly siloed supply chain. We've got our own Australian standards, and we've got our own suppliers, and they were different. They were different to our codes, were different to the rest of the world. Now it's less so. We're getting a lot more material coming in from overseas, and I know that Mike said there's people from 14 different countries in this session. So I'm sure there'll be some people around the room who would understand what I'm talking about there. But there's more risk that comes with bringing materials in and not understanding their mechanical properties, or not understanding how those mechanical properties relate to how your own codes were derived in the first place. So in that, we did a recent project where we were bringing materials in from Korea, and we had a company called, I won't mention the name, but anyway, they in-country inspectors who were their job was to make sure that we were getting what we asked for. And I think that's a sign of the times going forward because of that globalisation of supply. And globalisation of design teams as well. I mentioned earlier the connectivity and the model sharing means that joint ventures are easier to make work. This can be across town or it can be across the globe. That is the end of my presentation. I touched on those topics of globalisation, of the drivers and communication, and I'd be happy to take any questions.
Mark, that's great. Thank you very much. We've got about 5 minutes where we can do some questions. The first one is from Knut Gopert at Schleichbergman. He says, Mark, regarding the retractable roofs you show, is the design of the driving principle driven by the engineering team or by an early contractor involvement? Is the design of the driving principle driven by the engineering team or by an early contractor involvement?
Yeah, good question, and good to hear online. So I think it's by the design team. Certainly in the projects that I've been involved in, it has, and that's because the geometry of the structure generally can dictate what sort of mechanism you might use. In a lot of the ones that we've done, we've had flat roofs or flat rails, and that allows the ability to use wheeled solutions. Having said that, I've done 2 projects that had cogged wheels and ran on sort of tooth rails as well. So there's lots of different ways to skin a cat. Often, it depends at what stage the contractor gets involved in the project as well. But it's the mechanical design component of those roof structures quite complex, and as I said before, my colleague and I have done it quite a few times before, so we kind of understand. I understand his mechanical constraints, he understands my structural constraints, and we tend to get by. But good question, thanks, Nick.
So I have one for you, and Mark, and that is to do with the crabbing. I mean, normally trying to get 2 sides of a roof to move exactly at the same time is really difficult. Do you have a sort of a guide for the amount of angle you let it twist, or how do you decide how much crabbing is going to be acceptable, and how do you control that?
Yeah, look, really good question. The simplest one is a roof that is on, say, 4 bogies, 2 bogies at each end, and we would put only have one of them that was fixed and have the other 3 on sliding bearings, so that the roof itself is able to rotate. As it rotates, it starts throwing horizontal forces into the structure, but you're only sort of fixing at one point. So if you try and fix 2 of those bearings, which is probably where your first thought would be, I'll fix 2 of them, I'll have the other 2 sliding. Well, as soon as you do that, then you can start having some magnified forces. But basically, if you only fix one of them and have the other 3 sliding, then the maximum horizontal force you can put into your structure is just the product of your axial force going into the top of the bearing times your friction force on the bearing is the horizontal force that's going to go into the structure. And
I guess thermal loads then are taken out by that system as well. So you avoid
same system, yes. If you only got one locked in, then thermal loads, and once again, all the loads, the thermal load still becomes a factor of the gravity load times your friction factor. So it's actually quite simple.
We're nearly out of time. I don't know whether you can give us an idea of the steel grades that you used. That would be quite interesting. Certainly on the long span truss 167, I guess.
Yeah, they were. You're testing my memory, but they were 610 diameter, and the maximum thickness was 56 millimeters, and I think it was grade 400 steel. Right. That was last time I looked at that would have been 21 years ago. So that's an educated guess.
We can get some better steel now, so that's a chance to make things even smaller in the future. Mark, that's fantastic. I hope you'll stay around. There's a question and answer session a bit later on, and also a chat afterwards as well on Zoom. So thank you very much for that.